we said that accuracy on its own wasn't the best metric because you could get 91% accuracy but still have a lot of undetected COVID cases. It turns out that recall is also not perfect. Okay, can you think of a way to invent a COVID test that achieves 100% recall? Remember, it goes between 0 and 1, or 0 and 100%. How could we get 100% recall? Yeah, if we just say everyone has COVID, then everyone who does actually have COVID, we will correctly identify. Do we agree? In other words, we will have no false negatives. There will be no one who has COVID and we say they don't have it, because we're saying everyone has it. Okay? And so we can always achieve 100% recall. We can do that just by predicting the positive class, or predicting 1, predicting you have COVID. Okay, and so now I've drawn a new confusion matrix for our everyone has COVID classifier. And notice there are no numbers in this column because we're not predicting the negative class at all here. Right? Negative here is not COVID. But we're saying everyone has COVID. So all of our predictions lie in the right column. And so all of my predictions are either a true positive, meaning they had COVID and I said they had it, or a false positive, meaning they didn't have COVID and I said they did. Okay? So firstly, are we comfortable with this being the confusion matrix for the everyone has COVID classifier? You comfortable with that? Okay. And so the recall of this new classifier is 1. Everyone who had COVID we sort of captured and identified. But what's the issue with this classifier now? What's the issue? Yeah. Yeah, it has 91 false positives, which means for 91% of data points, it just said people had COVID when they actually didn't, right? And so that's not great either. Even though it seems more important to sort of, here's what I'm trying to say. The most important thing for our classifier is identifying when people have COVID. But if to do that, we need to say 90% of people also have COVID when they don't, that doesn't really seem like a fair trade-off. Right? So it seems like we need some way of measuring sort of the fact that we have a ton of false positives as well. And so there's another metric that we can use here called precision. Okay, so notice when we computed recall, we looked at the actually positive row. Right? We were looking at all of the individuals who actually had COVID. When we look at precision, instead we are looking at the positive column. Or more specifically, we are looking at all of the individuals who we predicted to have COVID. Okay? And so precision, like recall, is another ratio. But here, the numerator is still the true positives, but the denominator is the total number of individuals who we predicted to have COVID. Okay? In recall, the denominator was the number of individuals who actually had COVID. In precision, the denominator is the number of individuals who we predicted to have COVID. Okay? And so people, often find it difficult to remember sort of the difference between precision and recall because they look kind of similar. And here's the best way to remember them. In precision, both terms in the denominator have a p, and precision also starts with p. Okay, so precision, all of the terms involve a p. That's not true for recall, right? Because for recall, the bottom right number will be false negatives. Precision, you have true positive plus false positive. Okay? All right, so what's the precision of the everyone has COVID classifier? 9%, right? It's not very precise, right? It's capturing everyone who actually has COVID, but it also captured a bunch of people who don't have COVID. And that's not great. Okay? So it seems like, recall is important, and precision is also important. And so ideally, both of these numbers would be at 1 or 100%, right? Because these are both good things, right? We want precision to be high, we want recall to be high. But as you can imagine, if you want to increase your recall, that often comes at the cost of decreasing precision and vice versa, right? It's kind of like sort of this balance. It's not quite the same thing, but it's similar to this trade-off that we weighed when looking at cross-validation, right? There's like a sweet spot that you want to arrive at And if you sort of want a sort of more complicated model, you have to put up with more model variance, for instance. Okay, and we will weigh this trade-off between precision and recall in just a bit. What I want to point you to is this really nice chart put together by Wikipedia. Wikipedia actually has like very, very good illustrations for precision and recall. And so here it like graphically shows us the definition of precision and the definition of recall. Notice the numerator is the same in both. It's the true positives, right? It's the positive elements that we like correctly classify. In recall, the denominator involves the false positives. So those are the things that we are predicting to be in class 1. And in recall, we're involving the individuals that are actually positive. Okay? Sound good here? All right. So what I want to do is think about sort of conceptually when we would prefer models with high precision and when we would prefer models with high recall. So can you think of an example of a classification task where high precision is more important than high recall? Can you think of an example? When might high precision be more important than high recall? Yeah. Go for it. I think I kind of get what you're saying, but that is not quite what I was expecting. But I get what you're saying. If I'm understanding correctly, you're saying if we're building a classifier that like looks at a planet and predicts whether or not we could live there, you want to be really sure if you're predicting that we can live there, that we can actually live there. Right, exactly. Does anyone have another example along those same lines? Where like if we predict the positive class, we want to be really sure about that prediction. Yeah. Right. In all of these examples, the common thread is you really don't want a false positive, right? Another example is if you're predicting whether someone, that's a weird example to use, but if someone committed an academic integrity violation, right? You don't want to falsely accuse someone who didn't actually commit a violation, right? So you want a model that is really precise there. Do we agree? Okay. So we really want to avoid false positives. Remember, if false positives are small, this fraction is big. Do we agree? Okay. When might we want high recall? Like when might we prioritize high recall over high precision? Yeah. Yeah, in any sort of medical test, right? Even COVID detection, right? Here, like, if we want to prioritize recall, it means the cost of a false negative should be really high. Right? And if you think about a medical case, like if you go and sort of get diagnosed for cancer or COVID or whatever, you really want the test to identify if you actually have the disease. Right? So a false negative would mean you have the disease, but the test said that you didn't. And that would be really bad in the medical setting. Do we agree? Right? And so in the medical setting, we really don't like false negatives, and so we want our recall to be high. Okay, so are we clear on sort of the differences on when we'd prefer higher precision versus higher recall? Right? And the issue with accuracy is that it doesn't look at these nuances at all, right? Accuracy just looks at what proportion of your predictions were right. But two classifiers could have the same accuracy but very different precisions and recalls. Okay? That's why we're looking at this in the first place. All right. So we don't have a ton of time. But what I've done here is I've put together a practice confusion matrix, and sort of your task here is to calculate the accuracy, precision, and recall using this confusion matrix. Now, we don't have enough time to sort of work through the examples on our own, but if you click these arrow buttons here, it'll show you the answers. Okay, so what you should do is go home and use this to practice for your exam. Sound good? Okay, don't forget to do that. Otherwise, you'll be sad on Saturday. Okay. So that's it as far as content that is in scope for the final. Okay, so the remainder of the content that we're going to talk about today is still relevant for Project 5 and relevant I don't know if you care about data science, but it's not going to be on the exam on Saturday. Okay? All right. So we just used sort of predicting cancer as like a case where we would want high recall. Right? We want to be really sure that we can identify cases where people have an underlying disease. And so to illustrate how that might work, let's look at a tangible example. Okay? So if you've sort of read about, if you've read like machine learning tutorials online, a data set that is commonly brought up is the Wisconsin breast cancer data set. Has anyone heard of that before? No? Okay. Anyways, it was put together by the University of Wisconsin in like 1990. Okay? And it sort of contains several measurements that were sort of obtained by X-rays. Okay? So like, I don't know, mean radius, mean texture, mean perimeter, mean area, so on and so forth. And the labels that it contains are either 1 or 0. So 1 here stands for malignant, and that refers to a tumor that can spread to other parts of your body, and that's sort of cancerous. And 0 stands for benign, which is a tumor that, you know, while it may be big, it doesn't spread to other parts of your body. Okay, so these are measurements of tumors. Sound good? Okay, and so our goal is to use all of these features, mean radius, mean texture, mean perimeter, to predict whether or not the tumor is malignant. Okay, but when I say malignant, just think cancerous. Okay? All right. I'll point out that this data set, it is built into sklearn.datasets. That's how commonly it is used. And like when you load it, it gives you this dictionary with a whole bunch of information. So if you want to know sort of who collected it, why they collected it, whatever, all of that information is there for you. Okay, so whenever performing binary classification or classification more generally, it's always a good idea to look at the distribution of the response variables, the distribution of the y's that you're trying to predict. And so here we can see that in the entire data set, 37% of the tumors were malignant and 62-ish% were benign. So if we build a classifier, what should its accuracy be at least? Yeah. Right, it shouldn't be less than 62%, because we could get that by just saying no one has a cancerous tumor. Okay, so it should be better than that. But remember, we're not looking at just accuracy, we're looking at these new ideas, right? Precision and recall. And again, which one seems more important here? Recall, right? We want to be able to identify cases where patients have a malignant tumor, because when we identify that they have a malignant tumor, that means we can send them in for more testing and so on and so forth. If we think they don't have a malignant tumor, well, then that can be really bad because their cancer could go undetected. Right? So here, recall would be more important. Okay, so we could just use, you know, a decision tree classifier or a random forest classifier, but I think this is actually a good opportunity to briefly introduce another type of classification technique, and this is one where you have a very nice control over the balance between precision and recall, and it's called logistic regression. Now, this may seem a little strange, because I said it's a classification technique, but it is called logistic regression. That alone should sound a little weird, right? Because regression, we predict real numbers, classification should be 0 or 1. How does that work? Well, let's take a look. What logistic regression does is kind of like an extension on top of what linear regression does. That sort of piece here that is underlined, that should look like a linear regression model, and that's because it is. Right? A linear regression model, it's an intercept plus a bunch of features times slopes. That part seems familiar? Okay. What a logistic regression model does is it predicts the probability that a data point belongs to class 1. Okay, and remember here, class 1 is the positive class. In our example, that would be a malignant or cancerous tumor. Agreed? So what this is doing is it's going to take in a patient's sort of tumor's mean radius and mean texture and mean diameter, whatever, and it's going to predict the probability that the tumor is cancerous. We agree? Okay. Does anyone know what this weird symbol here is? Yeah, it's the sigmoid function. Right? As we know, in linear regression, our predictions can be any real number. They could be positive, negative, they could be 1,000, negative 200. But I said that logistic regression is predicting probabilities. And probabilities need to be between 0 and 1. So you can think of this sigmoid function as being like this squeeze operation that takes your line and squeezes it to be between 0 and 1. That's kind of an oversimplification, and there's sort of more theoretical reasons as to why we use a sigmoid, but that explanation will work for now. And so all the outputs by this model will be probabilities that we can sort of interpret as being the probability of class 1. Agreed? Okay. So this is where the strangeness of the word regression and logistic regression comes into play. I said it's a classification technique, but then I also said it predicts probabilities. So what if our logistic regression model predicts that the probability that a tumor is cancerous is 75%? What classification do we make? Or what if it gives us a predicted probability of 30%? What classification do we make? Yeah. You're getting one step, you're right, but you're sort of one step in the future. How do we go from these probabilities to predictions? You said it, but what is it? How do I go from 0.75 to malignant or not? How do I go from 0.3 to malignant or not? Yeah, we just set a threshold, right? So we take these probabilities that logistic regression computes and say, okay, if the probability is above, say, 50%, we're going to predict class 1, malignant. If it's below 50%, we're going to predict class 0, or benign. Sound good? Okay. And so, if we pick the threshold 50%, which is not the only threshold you can pick, we would get 1 for the 75% prediction and 0 for the 30% prediction. Sound good? Okay. So let's look at how this works under the hood. So I'm importing logistic regression. Notice I'm importing it from the same place we imported linear regression, which is linear model, because they're both linear. I'm going to perform a train test split. I'm going to instantiate my logistic regression, fit it with my training data, and I'm going to use it to make predictions for the y's for my test x's. And so what is strange to me is that this already gives us 1s and 0s. Even though I said this is a logistic regression model. Right? You kind of encountered this in lab 9. Right? If you use decision tree classifier for something that involves regression, it doesn't quite work. Here it's called logistic regression, but it's classifying things, because the only outputs are 1s and 0s. Do we agree? And so that has always been a little strange to me, but what sort of makes it make sense is that there is also a predict probability method, where I can see the probabilities that were predicted by this model. Okay, and let's take a look at how that works. So I'm going to use predict proba, because probability is too long to write. Oops. And we don't get back a list or array of single probabilities. We actually get back a 2D array of probabilities. Why do we get back a 2D array? Yeah, what this is doing is it's giving us the predicted probability that this data point belongs to class 0, and the predicted probability that this data point belongs to class 1. Which means if I add up the elements in these individual lists, what should I get? 1, right? It should be 1 no matter what. And we can hopefully verify that. And you see that, right? Because it's adding the probability of class 0 and the probability of class 1. Now, we only really care right now about the probability of class 1, so I'm just going to index into here and get my probabilities of class 1. And so under the hood, what sklearn is doing is it's thresholding automatically. So it's comparing all of these numbers to 0.5, and it's turning them into trues and falses. And just because I want to be certain that this is exactly what predicted, we can compare these two. So this is what predict was doing automatically. This was our sort of manual method, and you can see all of the entries are true. So that's all it was doing. It was predicting the probabilities and using a threshold of 0.5. Agreed? Okay. I'll also point out that our model still has W's, or W stars, right? It still has intercepts and coefficients. They're just part of this sigmoid function now, but you can access them if you needed to. Okay, so it's not really that different than linear regression. Okay, the mechanics of logistic regression are not really the point. Let's look at how well our model did. Okay, and so what I'm going to do is use these built-in accuracy, precision, and recall metrics here. Okay, and how did our model do? Did okay as far as accuracy goes, right? precision too, right? We got 98% precision, which means 98% of the time, if we predicted someone's tumor was cancerous, it actually was cancerous. But the recall is a bit low, right? We're actually, amongst all of the people who actually had cancerous tumors, we only successfully identified 87% of them. Do we agree? So that's a little low, and ideally we can bring that up. And so as you will see, by sort of tweaking our threshold, we will be able to tweak the precision and recall. Okay, and we're getting there in just a second. One thing I'll point out is that sklearn.metrics has built a built-in confusion matrix method, and you sort of interpret this the same way that you interpreted the manual ones that I created before. But looking at these numbers on their own is kind of, 20th century. We can draw a plot here. Okay, so this is called plot confusion matrix, and it sort of visualizes the exact same numbers. So bottom right, we have our true positives. Top left, we have our true negatives. Top right, we have the cases where we predicted positive, but it was actually negative. So those are false what? Top right, what do we have? False? False positives, right? Because we predicted positive, and then bottom left must be false negatives. Yeah. Yes, so if you have the lecture notebook open, you'll have different numbers, and it's because the train test split is random, right? And so that's why I have different results. You may have noticed sometimes in lecture I'll add random seed equals something, and when I add that, then you will always get the same results as me, but there is no need to do that really here, and so that's why you'll see different numbers. Okay, so the train test split was different, the coefficients were different, probabilities were different, and so the confusion matrix is different. But it shouldn't be that different, right? The colors should probably be the same. Okay. All right, so here's the confusion matrix for our default classifier. We didn't change the threshold at all. It uses 0.5. And actually, it uses 0.5 by default, and there's actually no way to change it to use something else. If you want to use a different threshold, you have to manually implement that. I'll talk about why in just a second. But first, let's think conceptually, right? Right now, we've been saying we will predict that someone's tumor is cancerous if the probability was above 0.5, or greater than or equal to 0.5. And we will say it was not cancerous if the probability was below 0.5. What do you think would happen to our precision and recall if we increased the threshold? So if we increase the threshold to, 0.6, 0.7, 0.8, what would happen to the precision? Not quite. So if we increase the threshold, we're setting the bar for making a positive classification higher. Because with 50%, there's a larger chance that we make false positives. But if we increase this bar, then anything that exceeds that bar is likely to be a true positive. Do we agree? So if we sort of increase the threshold, we're going to decrease the number of false positives, which means our model's precision will increase. Do you sort of see that? Right? Because we're being more selective about what counts as a positive prediction. But what's going to happen to the recall if we increase the threshold? It's going to decrease, right? Because there will be more and more false negatives. What about people who actually had cancerous tumors, but their predicted probability was only 0.49 or 0.51 because the model is not that great? Right? Then we will raise the threshold to be higher than what their predicted probability was, leading to a false negative. Right, so are we comfortable with the fact that as we increase our threshold, precision will increase, but recall will decrease? Okay. And as you can imagine, if you were to decrease the threshold, the opposite effect would happen. You decrease the threshold, your recall goes up because you're capturing more true positives, but you're also capturing more false positives, and so your precision decreases. Sound good? Okay. So, like I said, the threshold is not actually one of the hyperparameters you can tune here, right? If you look closely, threshold is not one of them, okay? And in fact, I don't even think the documentation explicitly says that it uses 0.5. It just does. I mean, we verified it, right? And the reason for that is because the threshold doesn't actually change the W's in your logistic regression model. All of those other hyperparameters you could choose do change your W's, and so they do change sort of how well your model would work on unseen data. But the threshold doesn't change how well your model works on unseen data. It just changes sort of its balance between precision and recall, which is outside of the scope of fitting the model. Okay? So that's why threshold is not one of the hyperparameters you can tune directly, but it's still a hyperparameter. You just have to sort of tune it manually. And so what I've done here is for every threshold between 0 and 100%, I've sort of executed that threshold myself and computed the resulting precision and recall. So now we can look at, say, the relationship between precision on the y-axis and threshold on the x-axis. And as we predicted, as the threshold increases, the precision increases. Because as the threshold increases, we are like raising the bar for what counts as a positive prediction, and so we will have fewer and fewer false positives. So are we comfortable with why we are seeing this graph? Threshold goes up, the precision goes up. Sound good? Okay. As I mentioned, we will see the opposite effect with recall. So now, as we increase our threshold, the recall will keep going down, meaning we're going to have more and more false negatives, right? Because there are people who, actually have the disease, but their predicted probability just happened to be low. And if we increase the threshold above them, then we're just incorrectly classifying those people who have the disease, right? So are we comfortable with why the threshold increasing leads to the recall decreasing? Okay, good. And so we looked at these precision and recall curves separately. What we often do is just plot recall on the x-axis and precision on the y-axis. It's kind of an arbitrary choice. We could do the other way around as well. And what we have computed is called a precision recall curve. Okay, so recall is on the x-axis, precision on the y-axis. And so now we can sort of see the trade-off between precision and recall. Okay? Now, the threshold itself, that does not appear on this plot. But the threshold increases either this way or this way. Which way does the threshold increase? Where is the threshold equal to 0? Where is the threshold 0? Yeah. Yeah, the threshold is 0 when you've sort of correctly identified all people with cancerous tumors as having cancerous tumors. So the threshold is 0 when your recall is 1. Do we agree? And the recall is 1 down here. And actually, the way I've set it up is that when you hover over a point, it tells you the threshold. But here, you see the threshold is 0. So the threshold actually increases till we get over here, and here we have a threshold of 1. Okay? So the threshold is going up this way. Do we agree? Okay. So given what you know about precision and recall and the particular task we are working with, what threshold would you pick, or how would you pick a threshold? I guess, firstly, if we had like the world's most ideal threshold, where would its point on the graph be? Where do we want our classifier to be? Yeah, here at the top right. Because the top right here, that's 100% precision and 100% recall. That's what we want. Right? So one strategy for picking a threshold might be to just say, okay, what point is closest to here? Either in terms of sort of Euclidean or L2 distance, or just by looking at it. Right, so maybe I picked this. But then remember we said that we really prioritize recall, and so visually I might say, okay, I might go with this model, for instance, or this threshold, for instance. Right? And sort of as we predicted, we would probably lower the threshold for making a positive prediction here, because we want to be sure that if someone has a cancerous tumor, we identify that and send them for more screening. Right? And in this case, it's actually okay if we come up with a false positive, because in the additional screening we send them to, the fact that they were a false positive will probably be detected. Right? Whereas if they're a false negative, we're going to send them home. There's not going to be any additional screening, and that could be bad. Okay? So any questions with this precision recall curve? Okay, and I know we're just sort of glossing the surface here. This is not part of your exam, but you will learn about this in future ML courses, and you will learn about this measurement called the AUC. That's called the area under the curve. Okay, and like one sort of calculation you could compute is what the area under this blue curve is. And ideally, that would be close to 1, because if the curve went through this point, 1, 1, it would mean there was some threshold that had perfect recall and perfect precision. Okay, so that's a PR curve. I'll also quickly note that you might think of precision and recall as both being equally important. And so it turns out the correct way to combine your precision and recall is not to take the arithmetic mean, but to take what's known as the harmonic mean, which is how you sort of take the average of two rates. Right? Similar if you wanted to say, like, I drove at 48 miles an hour for 30 minutes and then 60 miles an hour for 30 minutes. What was my average speed? It's not the average of 48 and 60. You'd have to do a bit more of an elaborate calculation. Same rule applies here. But anyways, the sort of algebraic form of it is here. It's 2 times the product over the sum, and that is called the F1 score. So the F1 score is like a one single measurement that represents your model's precision and your model's recall. Okay? Note that this might seem similar to accuracy. But remember, accuracy doesn't take into account the kinds of errors your model made, whereas precision is penalized when we have false positives, and recall is penalized when we have false negatives. So the F1 score and accuracy, while they seem similar, and in this case they are similar, they're not quite the same thing, because the F1 score prioritizes sort of the different kinds of errors that your model could make. Sound good? Okay, and if you look at the Project 5 write-up, one of the questions says, like, why did you choose accuracy versus F1 score? And this is what you would look at if you wanted to pursue that. Sound good? Okay, remember, accuracy, not good when there's class imbalance. Lastly, I'll point out that Wikipedia has this massive table of like other classification evaluation metrics you could use. We just scratched the surface, right? We just talked about recall, which is also called true positive rate here, and precision, which is also called positive predicted value. Now, what really annoys me is, depending on the site you go to, you'll come up with a different name for each of these things. So recall, sensitivity, and true positive rate all mean the same thing. Now, I intentionally didn't bring that up because it would just be harder to remember. So you just have to think about recall and precision. But my point is there are a variety of other similar metrics. But if you think back to the confusion matrix, everything we computed involving summing either a row or a column. But we only summed one row and one column. There were other things we could have summed and other things we could have put on the numerator. And that's what gives way to these other metrics.